Right now, wherever you are, it feels like there is one shared moment unfolding. Time seems like a river carrying everything from a finished past into an open future. That sense is so basic, we almost never question it. Yet in modern physics, this picture does not survive. When we look closely at space and time, past, present and future start to look equally real, and the flow of time begins to look like something our minds create. In this journey, we will follow that idea to its strangest consequences. If you enjoy exploring puzzles like this, make sure to like the video and subscribe so you can keep travelling with us. In everyday life, time feels simple. You glance at your phone, you see a number, and you trust that everyone else in your city is living through the same moment. If it is 3 in the afternoon for you, it feels natural to say it is 3 in the afternoon everywhere on Earth, and in some sense 3 in the afternoon throughout the universe. There is a past you remember, a present you occupy, and a future that has not happened yet. This picture is so deeply woven into language and memory that it seems almost silly to doubt it. For a long stretch of history, that everyday picture was not just common sense, it was official physics. In the 17th century, Isaac Newton described a universe with 3-dimensional space and a single, absolute time. In his view, time flows uniformly, at the same rate for everyone, everywhere, like an invisible cosmic clock ticking in the background. The present moment was a global slice of reality, a shared now that cut across the whole universe at once. The past was fixed, the future was open, and the job of physics was to say how matter moves through this fixed temporal stage. For more than 200 years, that framework worked astonishingly well. From falling apples to orbiting planets, from thrown stones to spinning wheels, Newtonian time and space explained almost everything people could measure. Engineers built machines, navigators crossed oceans, and astronomers predicted eclipses, all using the idea of a universal clock. No one needed to ask what it really meant for 2 events to be happening at the same time. That phrase seemed perfectly clear. 2 things are simultaneous if they occur at the same reading on the cosmic clock. End of story. Trouble began quietly in the world of electricity and magnetism. 19th century physicists discovered that light is an electromagnetic wave, and they measured its speed with increasing care. No matter how they set up their experiments, they kept getting the same answer. Light in empty space always moved at the same speed, about 300,000 kilometers per second. That was already strange enough, but the real shock came when people asked what that speed meant for different observers. In normal life, speeds add. If you walk along the aisle of a moving train, someone standing beside the tracks will measure your speed as the speed of the train plus your walking speed. If you throw a ball forward inside the train, an outside observer sees the ball moving faster than you do. This is how our intuition is built. It feels obvious that if you chase something, you reduce its speed relative to you, and if you run away from it, you increase it. That is why the constancy of the speed of light looked like a problem. Imagine running toward a beam of light with your fastest rocket, or racing away from it with all the fuel you can burn. According to classical intuition, the light should appear slower to someone chasing it, and faster to someone fleeing from it. Yet experiments say otherwise. No matter how you move, if you build a good enough clock and ruler and measure carefully, you will find the same speed for light. It is as if the universe refuses to let that number change, no matter what clever motion you try. At the start of the 20th century, a young patent examiner named Albert Einstein decided to take this weird result seriously. Instead of asking how to bend light to fit our ideas of time and space, he asked whether time and space themselves might need to change. He assumed that the basic laws of physics should look the same to any observer moving at a steady speed, and that the speed of light in empty space is the same for all of them. Then he followed the mathematics where those assumptions led. The destination was special relativity. Special relativity tells us that to preserve a constant speed of light, the universe must give up some of the things we thought were obvious. Distances can shrink depending on your motion. Time intervals can stretch. 2 observers who glide past each other smoothly, each convinced that their own clock is normal, can legitimately disagree about how long the same process took. Their measurements are not mistakes, they are built into the structure of reality. The idea that there is one master clock ticking out the same seconds for everyone begins to crumble. Hidden inside this shift is something even more unsettling. Our basic idea of a shared now depends on how we decide whether distant events are simultaneous. If you look up and see a flare on a distant mountain and a flash from a nearby streetlight, you might say they happened at the same time. In Newton's world, we could imagine sending that information to the cosmic clock and getting a clear answer. In Einstein's world, there is no such global referee. What counts as happening at the same time becomes entangled with how you are moving. This is not just a philosophical worry. The equations of special relativity give a precise recipe for translating between different observers' measurements of space and time. Built into that recipe is what physicists call the relativity of simultaneity. Two events that one observer judges to be happening at the same moment can be judged to occur in different order, or with a time gap between them, by another observer who moves differently. Both descriptions are correct within their own frame. There is no deeper fact that says one observer is right and the other is wrong. Up close, over human-sized distances, these differences are tiny. In a room, moving at walking speed, people will agree on what is happening now to within far better than a billionth of a second. That is good enough for conversation and coffee, so our intuitions survive. But the universe is enormous, and tiny timing shifts can be magnified across great distances. When you stretch the same equations across the gulfs between stars and galaxies, disagreements about what is happening now can grow from fractions of a nanosecond into minutes, days, or more. This is where the familiar picture of a single universal present begins to fall apart. If two perfectly reasonable observers, following the same physical laws, cannot agree on which distant events are happening in their present, then the idea of one shared now starts to look like an illusion. What feels like a single moving moment for you may slice the universe differently for someone who passes you on the street. In the next part, we will push this to an extreme, using a thought experiment with our galactic neighbour Andromeda, and see how strange the consequences really are. Picture two people walking past each other on a quiet city sidewalk. Nothing fancy, no rockets, no black holes, just ordinary human motion. One is walking toward the north, the other toward the south. As they pass, both look up toward the same patch of sky and wonder what is happening right now in the Andromeda Galaxy, our giant neighbour in space. According to the mathematics of special relativity, those two people can disagree about that answer by several days, even though they are only moving at walking speed. That is the Andromeda paradox. At first that sounds impossible. How could such a tiny motion change what is happening right now in a galaxy 2.5 million light-years away? The key is that this disagreement is not about what they can see. Light takes millions of years to travel from Andromeda to us, so whatever they see is ancient history. The paradox is about reality itself, about which distant events actually exist in their present moment. When they silently ask themselves what is happening there now, special relativity quietly gives them different, equally valid answers. To understand why, we need to think carefully about what we mean by now for distant places. In Newton's universe, the answer was simple. There was one absolute time shared by everyone and everything. If it is Monday at noon here, then it is Monday at noon everywhere else, even on the far side of the universe. In that view, teleporting to Andromeda and asking the locals for the date would give the same answer no matter how you were moving before you jumped. Simultaneity was an objective, universal relation between events. Einstein's theory breaks that picture in a very specific way. In special relativity, each observer has their own way of slicing space-time into past, present, and future. The rules for those slices come from how you synchronize distant clocks using light signals. You send out pulses of light, wait for reflections, and set clocks so that the speed of light looks the same in all directions. That recipe sounds innocent, but it ties your definition of now to your state of motion. Change how you move, and your plane of simultaneity tilts through space-time. Close to home, the tilt is tiny. Over the length of a room, two people walking past each other at a few kilometers per hour will disagree about which events are simultaneous with their meeting by an amount far smaller than a billionth of a second. No human sense or everyday device will notice. That is why it is so easy for us to carry Newton's picture around in our heads and feel that it works. For almost everything we do, it does work. Time feels universal because our lives are lived in a regime where the differences are ridiculously small. The universe, however, is not built to match our habits. When you stretch that same tiny disagreement over the distance to another galaxy, the numbers explode. The mathematical rule that relates time and space in special relativity says that the difference in what counts as now scales with distance. Double the separation, double the disagreement. Multiply the separation by millions of trillions, and the disagreement becomes huge. So those two people on the sidewalk, walking in opposite directions, carry with them two different slices of simultaneity that intersect Andromeda on different days. One of them, moving toward Andromeda, has a slice of now that leans forward into that galaxy's timeline. In their frame, some events in Andromeda that you might naturally call future are already happening. Perhaps in a classic version of the thought experiment, high-ranking officers there have already given the final order to launch an invasion of Earth. The other person, moving away from Andromeda, has a slice of now that leans backward. In their frame, those officers have not yet made up their minds. The debate is still going on. The order has not yet been given. Here is the uncomfortable part. According to special relativity, there is no deeper fact that says which of those pictures is really correct. Both observers are following the rules of physics. Both synchronize clocks in the standard way. Both calculate their version of now using the same equations. The theory does not secretly favor one and reject the other. If we insist on a single, global present, we're asking for something the theory does not provide. The structure of space-time simply does not include that extra layer of reality. It is tempting to shrug and say that this is just about language. Maybe we should just avoid talking about what is happening now in distant galaxies and focus only on what we can observe. But the Andromeda paradox keeps pushing back. These disagreements show up in the way the theory organizes events, even if no one ever looks at Andromeda. They are built into the geometry of space-time itself. If we want physics to describe what exists, not only what we see, then we cannot escape the conclusion that simultaneity at large distances is relative. Notice that nothing spooky or faster than light is happening here. No signal is sent. No one in Andromeda feels anything change. The two people on the sidewalk cannot use their disagreement to transmit information or win a lottery. The paradox is not about communication. It is about ontology, about what we say exists at a given moment. When that question no longer has a unique answer, the familiar picture of time as a single moving spotlight passing over a fixed universe begins to wobble. Some philosophers respond by insisting that there must be a hidden, preferred frame of reference. A real cosmic time that the equations do not reveal, but that quietly decides what is truly now. Others accept the relativity of simultaneity and retreat to a very local idea of the present, limited to what fits inside your immediate neighborhood. But many physicists and philosophers choose a different path. They take the relativity of simultaneity at face value and ask what kind of world would make sense of it in the cleanest possible way. That line of thinking leads toward a radical picture. Instead of a universe where only one thin slice of time is real at any given instant, we imagine a four-dimensional space-time where all events, past, present and future, coexist. Your now is just one way of cutting through that block. Someone else's now is another slice through the same structure. The Andromeda paradox then stops being a contradiction and becomes a clue. In the next part, we will step fully into that four-dimensional view and explore what it means to live in a block universe. By now, our picture of time as one shared moving moment is already shaky. The Andromeda paradox showed that different observers carry different versions of now, depending on how they move. If we try to hang on to a single global present, we find ourselves fighting against the structure of space-time itself. So what if, instead of patching up the old picture, we try something more radical? What if the flow of time is not fundamental at all, and what exists is something bigger and stranger than a moving three-dimensional world? A few years after Einstein published Special Relativity, his former teacher Hermann Minkowski offered a new way to think about it. He suggested that space and time are not separate arenas but part of one unified entity. In his famous lecture, he said that space by itself and time by itself fade away, and only a kind of union of the two will preserve an independent reality. That idea sounded dramatic, but underneath the rhetoric was a clear mathematical picture. Events in the universe become points in a four-dimensional space-time. Think about an ordinary event in your life. You're sitting in a chair watching this video on your phone. In Newton's world, we could describe where you are with 3 coordinates in space, then add a separate time reading from the cosmic clock. In Minkowski's world, those 4 numbers are not just a convenient way to label things. Together they form your space-time coordinates. The event that is you watching right now is a single point in this 4-dimensional structure. Your childhood, your next birthday, and your final day are all other points. Now imagine plotting your whole life inside this 4-dimensional arena. At each moment you have some location in space and some reading on a clock you carry. Draw a dot for each of those events and connect them with a smooth line. That line is your world line. It threads from the event of your birth, up through your early memories, through this particular moment, and onward into what you think of as your future. Every object has such a world line. Planets, stars, coffee mugs, cats, galaxies. The universe becomes a web of world lines woven through space-time. In this picture, motion looks different. Instead of objects moving through space as time passes, each object simply occupies a continuous path in space-time. A planet orbiting a star becomes a gently spiraling world line. A beam of light becomes a straight line at a 45-degree angle in a space-time diagram, always moving at the same speed through the combined fabric. History is not something being written as time flows. It is already there, as a fixed pattern in the 4-dimensional block. If that feels abstract, try another analogy. Think of a page in a comic book that shows a character in several panels. In the top left panel, the character is a child. In the next, a teenager. In the final panel on the page, they are older and facing an important decision. When you flip through the book, you experience the story in sequence. The panels seem to come alive one after another, but physically, all those panels coexist on the printed page. Nothing in the ink itself is flowing. The flow is in how you read it. The block universe picture says that reality is more like the printed page than like the flipping experience. Space-time is the whole book laid out. Your sense that only this panel is real, that the past panels have vanished, and the future panels do not exist yet, comes from the way your consciousness moves along your world line, not from the raw structure of the universe. The block already contains every panel, every event, every moment of every life. Past, present, and future are all equally there. Minkowski's geometry makes this idea precise. Special relativity tells us how different observers, moving at different speeds, relate their coordinates. Instead of one universal grid, each observer carries their own coordinate system through space-time. The laws of physics are written in a way that does not privilege any one grid. When you draw all the world lines in this geometry, you see that what changes from observer to observer is how they slice the block into what they call now, not which events exist. The block itself does not care which slices you choose. This is where the Andromeda paradox finds a natural home. In a block universe, you do not ask which Andromeda events are really happening now in some absolute sense. You ask how each observer's plane of simultaneity cuts through the block. One walker's slice intersects Andromeda at one set of events. The other walker's slice intersects it slightly further ahead or behind along its world lines. Both slices are just different ways of carving up the same 4-dimensional structure. There is no single magical slice built into space-time. From this point of view, the death of a universal now stops being a problem and becomes an expected feature. If space-time is the basic reality, then talking about the universe evolving from moment to moment is like talking about a map evolving from left to right. You can describe it that way if you want, but the map itself simply is. The same goes for the block universe. You can talk about things happening, about processes unfolding in time, but those are ways of describing relations between different events inside the block, not changes to the block as a whole. Of course, there is a big emotional cost to adopting this view. We like to think that the future is open, that tomorrow does not yet exist, that our choices help bring new reality into being. The block universe pushes against that intuition. In the block, the event of you deciding to watch this video, the event of you turning it off, your next big life choice and your final breath are all somewhere in space-time already. They are as fixed as the position of a mountain, even if you do not yet know where those events lie along your world line. It is important to notice what this picture does and does not say. It does not tell you that your choices do not matter or that you are a puppet. Your decisions are themselves events in space-time. They are part of the block. The structure of your character, your values, your thoughts, and your reasons are all woven into your world line. The block universe does not erase agency. It simply relocates it. Instead of agency being something that pushes the universe forward in time, agency becomes a pattern in the block that links certain events in a meaningful way. Seen this way, Minkowski's four-dimensional space-time is not just a mathematical trick or a convenient visualization. It is a candidate for what the world really is, a static four-dimensional structure in which all events are laid out. Einstein at first resisted this geometric view, but later embraced it. And he wrote to a friend that for those of us who believe in physics, the distinction between past, present and future is only a stubborn illusion. Minkowski's block gave him a way to make sense of that unsettling thought. In the next part, we will bring this picture into direct contact with the age-old debate about what really exists in time. On one side is presentism, the comforting idea that only the present is real. On the other is eternalism, the claim that the block universe is the true shape of reality. We will see how the relativity of simultaneity puts pressure on presentism, and why the block view, however strange, lines up so naturally with the geometry Minkowski and Einstein uncovered. Once you see the block universe on the table, an old philosophical battle suddenly feels very urgent. For centuries, people have argued about what really exists in time. One side says only the present is real. The past has slipped away and the future is still nothing at all. The other side says past, present and future all equally exist, just in different locations along a timeline. Special relativity does not end this argument by itself, but it changes the terrain in a dramatic way. The view that only the present exists is often called presentism. It matches our everyday feeling about time. You remember the past, but you cannot go back. You anticipate the future, but you cannot visit it. There seems to be a moving spotlight of reality that shines on one moment at a time. As the spotlight glides forward, new events come into being while old events drift into unreality. In this picture, the universe is like a film strip where only the frame currently in the projector is real. Eternalism is the rival vision. It says that the entire film strip exists. Past frames, present frames, and future frames are all equally part of reality. The moving spotlight becomes an illusion created by the way conscious beings move along their world lines. From the eternalist point of view, there is no deep metaphysical difference between a memory, this present experience, and a future event. They are just different points in space-time. What feels like the flow of time is more like the way your attention travels through a story that is already written. In a purely Newtonian universe, presentism can sit comfortably. If there is one absolute time for everyone, then it is easy to imagine that only the slice of the universe at that time is real. You can picture the cosmos as a three-dimensional stage that constantly updates itself. Yesterday is gone, tomorrow is not here yet, and only today exists. There is nothing in the old equations that pushes hard against that image. the tension comes when we take special relativity seriously. The key pressure comes from the relativity of simultaneity that we explored with the Andromeda paradox. Remember that in special relativity, different observers moving at different speeds cut space-time into past, present, and future in different ways. Their planes of simultaneity tilt relative to each other. Two events that one observer calls simultaneous can be placed in different temporal order by another. That is not a matter of clock error or confusion. It is how the geometry of space-time works. Now combine that with presentism. Presentism wants there to be one set of events that exist right now. It wants the universe to come with a privileged slice, the one true present, even if we do not know which slice it is. But relativity tells us that there is no unique, physically distinguished way to slice space-time into global moments. All inertial observers are on equal footing. Their frames are related by smooth transformations that preserve the laws of physics. The theory does not point to any hidden cosmic time that breaks this symmetry. A famous style of argument runs like this. Take two observers who move relative to each other. Each has a notion of which distant events are happening in their present. Now move along a chain of such observers, each slightly boosted relative to the last. As you go, the slice of simultaneity tilts bit by bit. By the time you reach a far distant galaxy, events that one end of the chain counts as in the distant past may be counted as in the distant future at the other end. If those chain steps are all legitimate frames, it becomes hard to keep saying that only one of them captures what really exists. One way presentists respond is to say that there really is a preferred frame after all. They might imagine a kind of hidden cosmic ether that defines true rest. In that frame, they say, there is a real objective present. All other frames are just convenient tools that blur this deeper structure. On this view, relativity is only a practical rulebook for observations, not a full description of reality. The cost of this move is that it quietly reintroduces something the theory worked hard to remove. It adds structure that plays no role in the equations. Another way presentists respond is to shrink the scope of the present. Instead of a global slice that spans galaxies, they focus on very small regions of space-time. Maybe only what lies within your immediate reach is truly present. Distant events are neither real nor unreal yet. They are outside the domain of existence. This saves the intuition that the present is special, but it makes reality oddly fragmented. What exists for you and what exists for someone else may no longer line up in a simple way. Eternalists look at the same situation and see an opportunity rather than a problem. If the laws of physics treat all frames equally, and if simultaneity at large distances is not fundamental but frame-dependent, then perhaps we should not build our metaphysics on the idea of a single present. Instead, the cleanest move is to say that all events in space-time exist. The different ways observers slice them into past, present, and future are like different ways of cutting a loaf of bread. The loaf does not care how you slice it. In this spirit, the block universe fits very naturally with special relativity. World lines and space-time diagrams already suggest a global four-dimensional structure. The relativity of simultaneity then stops being an objection and becomes a feature of that structure. You do not ask which slice is really now in an absolute sense. You accept that now is a local concept tied to an observer and that the deeper object is the entire block. Eternalism wraps this into a simple claim. Everything that ever happens at any time is part of the same existing space-time. Still, it would be a mistake to say that relativity conclusively proves eternalism and refutes presentism. The theory makes precise predictions about measurements of time and space, and those predictions match experiments extremely well. But how we translate that mathematical structure into statements about what exists is not uniquely fixed by the equations. Presentists can always add hidden ingredients, like a preferred frame, to salvage their view, even if those ingredients feel ad hoc. Eternalists can argue that their view is simpler and more elegant, but simplicity is a philosophical virtue, not a laboratory result. So we end up with a landscape where physics strongly suggests a four-dimensional space-time and the relativity of simultaneity, while philosophy wrestles with what that means for existence. Eternalism seems to take the hints of special relativity at face value and build a world picture that fits them neatly. Presentism pushes back, sometimes at the price of adding unseen structure. The debate is lively, and it touches everything from the nature of causation to the possibility of time travel. In the next part, we will turn back to Einstein and a remark of his that often appears in this debate. He once wrote that the distinction between past, present and future is only a stubborn illusion. We will dig into what he might have meant, how that remark connects to the block universe, and why the sense of flowing time feels so powerful, even if the equations remain silent about any cosmic flow. Einstein did not talk about the flow of time very often, but when he did, his words landed with a thud that people still feel. In a famous letter written after the death of a close friend, he tried to comfort the grieving family. He wrote that for those who trust the laws of physics, the distinction between past, present and future feels like a stubborn illusion. It was not a throwaway line. It was Einstein speaking from inside the space-time picture he helped create, trying to make sense of mortality and loss in a world where all events seem to coexist. On the face of it, that claim sounds almost offensive to common sense. How could the difference between yesterday and today be an illusion? Yesterday you were not doing what you're doing now. Tomorrow you may be somewhere else entirely. Your memories point one way, your expectations point another. The feeling that time flows from past to future is one of the most basic features of experience. To call it an illusion can sound like denying that experience altogether. So what could Einstein have meant? One way to approach his remark is to think about other illusions we already accept. Take solidity. When you knock on a tabletop, it feels hard and continuous. It stops your hand. Nothing about that experience suggests that the table is mostly empty space, with tiny particles separated by vast gaps on their own scale. Yet that is what modern physics tells us. The hardness you feel is an emergent effect of electromagnetic forces and quantum rules, not a fundamental property of continuous matter. The solidity is not fake, but it is not what it seems. The motion of the sun across the sky is another example. For most of history, it felt obvious that the sun moves around the Earth. You see it rise, climb, and set. You feel still beneath it. Only with careful measurements and new theories did we learn that the Earth spins and orbits the sun, and that the apparent motion in the sky is a perspectival effect. Again, the experience is real. The interpretation is wrong. The illusion lives in the story we tell about what we see, not in the raw sensations themselves. Einstein seems to be placing the flow of time in the same category. In the block universe view, all events in space-time exist in a four-dimensional structure. Your birth, this moment, and your death are all there as points along your world line. The laws of physics describe the relations between these points, but they do not single out one of them as the moving present. There is no special variable in the equations that plays the role of a universal now that sweeps forward. The sense of flowing from earlier to later is something added by consciousness. Calling it an illusion does not mean it is unimportant. Pain is also partly a construction of the brain, shaped by attention, expectation, and context. Yet it is about as real as anything we know. The point is that the brain does not give us a neutral, transparent view of reality. It gives us a useful, survival-oriented view. A sense of passage that organizes events into past, present, and future is immensely practical. It helps us learn, plan, and act. That alone is reason enough for evolution to build it in, whether or not time really flows at a fundamental level. The block picture helps explain why this construction might arise. Along your world line, there is a sequence of brain states, each one encoding memories of earlier states and predictions about later ones. At one point along that line, you remember being a child but do not yet remember being old. At a later point, you remember both. The pattern of memory content is asymmetric along the world line. That asymmetry gives rise to a felt direction from past to future. but the pattern itself is part of the static block. Nothing in the block is moving. Seen this way, the flow of time is like the sweep of a spotlight in a theatre, but the spotlight is not moving through the universe. It is moving through your representation of the universe. At one stage of your life, your attention and memory light up a certain stretch of your world line and its surroundings. At another stage, a different stretch. To the experiencing subject inside the story, it feels like being carried forward. To an imaginary external view that sees the entire block at once, it is just different points being illuminated in turn. This can sound cold and detached, yet Einstein reached for it in a deeply human context while trying to comfort a family dealing with death. In the block universe, the event of a person dying is not the annihilation of their existence. It is the last point of their world line. All the earlier points are still there in space-time. The child they were, the adult they became, every conversation and shared moment, all remain as parts of the block. They are not moving away from us into nothingness. They are fixed features of the structure. Of course, we do not experience those moments as existing all at once. We experience the loss intensely in our present. We cannot reach back and relive those earlier points in any practical sense. Physics does not hand us a time machine, so the comfort is subtle. It does not erase grief. What it offers instead is a different picture of what it means for a life to be real. Instead of a brief flame that appears and vanishes, a life is a whole world line laid out in space-time, with all its moments equally there. There is another angle on Einstein's remark. When he calls the distinction between past, present, and future stubborn, he seems to acknowledge how hard it is to shake the feeling of flow, even once you understand the physics. You can know in theory that time is part of a four-dimensional geometry, and still feel tomorrow rushing toward you and yesterday slipping away. The illusion is stubborn because it is wired deeply into perception and language. Every sentence you speak has a tense. Every story you tell has a before and after. So we end up with a kind of double vision. On one hand, the best supported physical theories point toward a block universe where all events coexist in space-time and where there is no fundamental moving present. On the other hand, our conscious experience insists on a flowing now and a sharp divide between what has happened and what has not. Einstein's line about illusion captures that tension in a single phrase. The flow we feel is not written into the equations, it is written into us. In the next part, we will lean into that personal side of the story. If the flow of time is a construction of the brain, how does the brain pull it off? We will explore the psychology and neuroscience of temporal perception, the idea of the specious present, and the ways neural circuits stitch together memories and predictions into a continuous story. The goal is not to diminish the experience of time, but to understand how it emerges for creatures who live inside a block universe without ever seeing the block from outside. So far, we have mostly lived in the world of equations and space-time diagrams. Yet the feeling that time flows is not written on blackboards. It lives behind your eyes. Even if the universe is a static block, you experience something very different. You feel a moving now, a sense that the past is fading behind you and the future is rushing toward you. To understand that feeling, we have to look inward, at the way the brain builds its picture of time. Right now, you do not feel a single razor-thin instant. You feel a short stretch, a living window with a little thickness. You can still hear the echo of the last sentence while the current one arrives. You see motion as continuous, not as a flicker of separate snapshots. Psychologists sometimes call this the specious present, a brief interval that feels like the true now. It is not a mathematical instant. It is more like a bubble of a few seconds that your mind treats as one unified moment. Imagine listening to a melody one note at a time. If your brain took in only an instant with no memory, you would hear nothing but detached sounds. The tune would vanish. Instead, your brain keeps a rolling record of the very recent past and blends it with the immediate present. This rolling record is part of what makes the world feel like it flows. Vision works the same way. When something moves across your field of view, your brain stitches together a series of changing images into a single smooth motion. Under the surface, neural machinery is working hard to make this possible. Different regions of the brain are sensitive to different timescales. Some circuits track very short intervals, like the time between notes in a piece of music or the milliseconds between sounds in speech. Others track longer stretches, like the time between meals or the rhythm of your daily routine. Networks involving the hippocampus, the frontal lobes, and deeper structures help you order events, judge durations, and form memories of sequences. Researchers have found neurons that change their activity in a way that seems to mark time. These so-called time cells fire in a pattern that unfolds across a delay, as if they are painting a little timeline of what just happened. Together, populations of these cells can encode how long ago an event occurred, or how far along you are in a short waiting period. They act like internal sand timers that your brain can read out when you need to know whether the light turned green a moment ago or several seconds ago. At a larger scale, your sense of time also depends on memory. When you recall what happened earlier in the day, you're not reaching back into the past itself. You're reactivating patterns of activity that stand in for those past events. The brain tags these patterns with order and context. It knows that breakfast came before your commute, and that both came before you started this video. That ordered chain of memories gives you a feeling of having moved from then to now, even though all of those memories are being reconstructed in this moment. Prediction plays an equally important role. Your brain is constantly forecasting what will happen next. When you catch a ball, you do not just react to where it is. You predict where it will be in a fraction of a second. When you listen to someone speak, your brain anticipates upcoming syllables and words. Many theories of perception suggest that the brain is always running a kind of internal simulation of the near future and comparing predictions with incoming signals. This constant forward-leaning stance builds a sense of direction into your experience. Put these elements together and a pattern emerges. Along your world line in the block universe, each brain state carries memories and records of earlier brain states and predictions about later ones. That asymmetry in content creates an asymmetry in experience. At one point you remember being younger and have certain expectations about being older. At a later point you remember both youth and middle age and have different expectations. The feeling of moving from past to future is a reflection of how those patterns are arranged, not a sign that the block itself is shifting. Notice also how your sense of time can stretch and compress. A boring meeting can feel endless. A joyful day can vanish in what seems like a breath. In danger, everything can slow down. People report that during accidents or falls they felt as if the world moved in slow motion. Yet the real physical time measured by clocks did not change. What changed was the rate at which the brain sampled and stored information. Intense situations often lead to denser memories, so when you look back, there is more packed into that interval and it feels longer. You can see smaller glitches in everyday situations. When you look at a clock with a ticking second hand, sometimes the first tick you see seems to last longer than the others. This odd effect, often called the stopped clock illusion, arises because your eyes made a quick jump and your brain filled in the gap with a bit of earlier information. Your experience of the first tick is stretched backward, making it feel longer than it really was. Again, the brain is not a passive recorder of time, it is an active editor. Even the boundary between now and not now is something the brain draws, not something you directly sense in the world. There is no special colour or sound that marks the exact edge of the present. Instead, your nervous system groups inputs into chunks, aligns them, and presents them as a unified moment. The chunk size depends on the task. For speech, the window needs to be tuned to the rhythm of syllables. For music, it may be tuned to the beat. For visual motion, it may be tuned to the speed of objects you normally track. All of this suggests a striking conclusion. The flow of time you feel is a story your brain tells, constructed from overlapping processes of memory, integration, and prediction. That story is tuned for survival. It helps you dodge cars, follow conversations, plan meals, and remember who you are. It does not try to reveal the deep structure of space-time. In fact, there would be no evolutionary advantage in perceiving a four-dimensional block. Creatures like us need to act in a local environment, not contemplate the full geometry of the cosmos. This is not a glitch. It is a feature. Your experience of time is like a user interface for reality, not a raw access to its code. Just as a computer desktop hides the messy details of transistors and voltage levels behind icons and folders, your temporal sense hides the detailed structure of space-time behind an intuitive feeling of flow. The illusion, as Einstein called it, is a very useful one. It lets you navigate your life without ever realizing that in the underlying physics, the block simply sits there. In the next part, we will widen the lens again and reconnect your inner sense of flow with the outer universe. We will look at why time has a direction at all, why we remember the past and not the future, and how the second law of thermodynamics and the growth of entropy carve an arrow of time into the block. Your brain rides that arrow as it tells its story, but the arrow itself is written in the large-scale structure of matter and energy in the cosmos. When you watch the world, it is easy to tell which way time is running. A glass falls off a table, shatters on the floor, and the shards scatter. Ice cubes melt in a drink. Cream spreads through coffee. If someone played those scenes in reverse, you would notice instantly. Shards jumping together into a perfect glass, melted ice reassembling into sharp cubes, coffee unmixing into black and white layers. Nothing in your experience looks like that. The world has a clear direction from past to future, yet at the level of basic laws, that direction almost disappears. Many of the fundamental equations of physics work just as well if you reverse time in them. If you film two atoms bouncing off each other and then play the film backward, the reversed motion still obeys the same rules. The equations do not care whether you run them forward or backward. That creates a puzzle. If the microscopic rules are so symmetric, where does the obvious one-way arrow of time come from? The key idea that helps resolve this is entropy. Entropy is often described as a measure of disorder, but a more precise way to think about it is as a count of how many microscopic arrangements correspond to what you see at the large scale. Take a box of gas. At the large scale, you might say the gas fills the box evenly. At the microscopic level, that could be realized by an enormous number of ways to arrange all the molecules. That kind of state has high entropy. Now imagine all the gas crowded into one corner of the box, leaving the rest empty. At the large scale, that is a very specific situation. There are far fewer microscopic arrangements that match it. That means it has low entropy. If you poke a hole and let the gas spread out, it will almost certainly move from the crowded corner state to the even spread state. Not because the laws forbid the reverse, but because there are unimaginably more ways to be spread out than to be squeezed into the corner. This is the heart of the thermodynamic arrow of time. Systems tend to move from states with fewer microscopic arrangements to states with vastly more, from low entropy to higher entropy. You can scramble an egg in countless ways, but there are very few microscopic patterns that count as a neatly separated yolk and white in an intact shell. So in practice, eggs break and mix. They do not unbreak and sort themselves. The forward direction in which entropy rises is the direction we call the future. Notice that this arrow does not come from some new force pushing things along. It comes from counting. The equations allow both directions, but starting from a special low entropy arrangement, the odds are overwhelming that the system will wander into higher entropy states and stay there. You could wait many times longer than the current age of the universe and almost never see a shattered glass spontaneously reassemble. It is allowed in principle. It is just insanely unlikely. This raises an important question. If high entropy states are so much more common, why is the universe not already in a boring, maximally scrambled condition? Why do we have organized structures at all? Stars, planets, temperature differences, living beings. The usual answer is that the universe began in an extraordinarily low entropy state. Very early on, matter and energy were arranged in a highly ordered way by cosmic standards. This assumption is often called the past hypothesis. According to this idea, The Big Bang was not just the beginning of expansion, it was the beginning of a special kind of order. From that special starting point, gravity and other forces could gradually turn simple early patterns into stars and galaxies, while also allowing local pockets of decreasing entropy at the cost of raising entropy elsewhere. A refrigerator reduces entropy inside its compartment, but increases it in the room through the heat it dumps out. Life does something similar. It builds structure locally while feeding off entropy gradients around it. From the past hypothesis, the arrow of time becomes a global pattern built into the structure of the cosmos. If you take any slice of the universe near that beginning and move forward along world lines, entropy tends to increase. Move in the opposite direction, and entropy would tend to decrease. So the distinction between past and future is not written into the basic laws, which are nearly time-symmetric. It is written into the large-scale boundary conditions of the universe. This helps tie together several different arrows that all point the same way. The thermodynamic arrow runs from low to high entropy. The psychological arrow points from remembered past to unknown future. The causal arrow runs from causes to effects, from striking a match to seeing the flame. All these arrows align because memory, information storage, and stable cause and effect relationships all rely on entropy increasing around us. Records of events are low-entropy structures created in a universe where there were gradients to exploit. In a block universe, this picture becomes especially interesting. The block contains an entire history with an entropy profile written into it. Near one end, the entropy is low, toward the other, it is higher. The arrow of time is then a gradient inside the block, not an external flow that moves the block along. At each point along your world line, your brain sits on one side of that gradient, with records of lower entropy states behind it and higher entropy states ahead. You ride the arrow but do not create it. From this standpoint, your feeling that the past is fixed while the future is open has a physical root. The past leaves stable traces, photographs, scars, memories, worn paths. These are low entropy arrangements that encode information about earlier states. The future has not yet left such traces in your present. You do not have records from tomorrow. In the block universe, tomorrow already exists as a region of space-time, but information from that region has not propagated back along your world line in a form you can interpret. It is worth stressing again that none of this requires a moving cosmic present. The laws describe how entropy is distributed across space-time and how world lines thread through those regions. The block is static in the sense that the whole structure just is. Yet within that structure, there are clear directions in which entropy rises. Those directions define arrows. Creatures like us, whose brains depend on forming and using records, naturally align their sense of time with the direction in which those records accumulate. So the arrow of time, which feels so fundamental in daily life, may be an emergent feature of statistics and an extraordinarily special cosmic beginning. It is not an extra law on top of physics, but a pattern that appears when you look at vast numbers of particles and the boundary conditions of the universe. In a way, the one-way street we experience is drawn by probabilities and initial conditions rather than by any single simple rule. In the next part, we will see how this picture extends into the full theory of space-time that Einstein later developed. Special relativity treated space-time as a flat stage. General relativity turns that stage into a dynamic, curved geometry shaped by matter and energy. We will explore how this curved block complicates our ideas of global time even further, and why slicing it into neat moments of now becomes even less natural, pushing us deeper into the block universe view. Up to now, our block universe has been living in the world of special relativity. Space-time was a flat stage where world lines traced out the motion of objects, and the relativity of simultaneity pushed us toward a four-dimensional view. That picture is already strange enough, but it is still missing something crucial. In special relativity, gravity is not really in the story. There is no account of why planets orbit, why light bends near stars, or why the universe expands. To bring those in, Einstein had to reshape the block itself. The leap he made with general relativity was to stop treating gravity as an invisible force that pulls on masses and to start treating it as the geometry of space-time. In this new theory, matter and energy tell space-time how to curve, and curved space-time tells matter and light how to move. Instead of world lines wandering through a rigid grid, they now follow the straightest available paths in a flexible dynamic fabric. The block universe does not go away. It becomes more intricate. Imagine laying a sheet of rubber on a table and scattering marbles on it. In the special relativity picture, the sheet is perfectly flat. Marbles roll in straight lines unless you push them. In the general relativity picture, heavy objects sink into the sheet and create dimples. Marbles that move near those dimples curve around them, not because a mysterious force reaches out, but because the straightest available path on the distorted sheet bends. Now translate the rubber sheet into four-dimensional space-time, and the dimples into curvature created by stars, planets, and galaxies. In this curved space-time, time and space are still fused, but they no longer come with a simple universal grid. The geometry can be different from place to place and from time to time. Near a massive body, clocks tick more slowly compared to clocks far away. Light beams that would travel straight in empty regions now bend as they pass through warped zones. Even the overall shape of the cosmos can change. In many solutions of Einstein's equations, the universe expands, so that distant galaxies recede from each other over cosmic history. This adds a new twist to our questions about global time. In flat space-time, we could at least imagine drawing a family of neat parallel slices and calling each one a moment of now for some nice set of observers. In curved space-time, that often becomes impossible. Many space-times simply cannot be sliced into a stack of global surfaces that every world line crosses once and only once. In some solutions, such as those that contain rotating black holes, there are regions where time and space effectively swap roles, and closed loops in time become mathematically possible. Even in friendlier cosmological models, the slicing is not unique. The expanding universe described by the standard Big Bang model is often drawn as a series of equal time slices. Cosmologists like to picture galaxies as raisins in a rising loaf of bread, with the dough between them stretching. There is a natural time coordinate linked to that expansion, measured by observers who float with the cosmic flow and see the universe as roughly uniform in all directions. For them, it makes sense to talk about the age of the universe at a given moment, but that cosmic time is not fundamental in the way Newtonian absolute time was supposed to be. It is a convenient choice that works well for a particular family of observers. A galaxy that moves in a slightly different way will not agree exactly on which events line up with which cosmic ages. And many general relativistic spacetimes do not resemble the smooth, expanding loaf at all. They might be lumpy, chaotic, or have weird topologies that resist any simple notion of a cosmic clock. From the block universe point of view, this is exactly what we should expect. If reality at its deepest level is the four-dimensional space-time itself, then any division into space and time slices is secondary. It is a way of organizing the block for particular purposes, not a feature that the block carries inherently. General relativity makes this even clearer than special relativity, because the geometry can flex and twist in ways that defeat any attempt to lay down a single universal time coordinate. World lines still exist, of course. Your world line, the world line of the Earth, the paths of photons streaming through space, all thread through the curved block. But they do so in a geometry that can focus them, stretch them, and sometimes trap them. Near a black hole, for instance, world lines that fall inside the event horizon cannot escape again. In the block picture, the entire history of those infalling paths, including their final plunge, is part of the structure. There is no sense in which the black hole is waiting to finish swallowing them. The swallowing is already in the block. The bending of light around massive objects gives a very visual example of the curved block. When light from a distant galaxy passes by a cluster of galaxies on its way to us, the cluster's mass curves space-time in its neighbourhood. Many different light paths can then lead from the source to our telescope. In the sky, we may see multiple images of the same galaxy, distorted into arcs or rings. In the block universe, those images correspond to distinct world lines of photons that all leave the source at different events and converge on our detector. The geometry of the block decides which of those paths exist. This curved view also deepens the relationship between gravity and the arrow of time. The early universe, in the standard picture, was not just hot and dense, it was also strangely smooth, with matter spread almost evenly. That smoothness represented a low entropy configuration for gravity. Over time, small irregularities grew, matter clumped, and structures formed. In the block universe, this story is a pattern etched into the geometry from one end of the block to the other. The growth of structure and the rise of gravitational entropy are part of the same four-dimensional shape. Once again, the laws of general relativity do not single out a moving present. They relate the geometry of space-time to the distribution of matter and energy across the entire block. Solutions to Einstein's equations are like fully drawn maps, not like evolving snapshots. When physicists solve these equations, they often specify conditions on a whole slice and compute the rest. But that is a method of calculation, not an assertion that the universe literally grows slice by slice. The solution itself is a complete space-time. So general relativity does not replace the block universe with something more familiar. It reinforces the idea that the block is the fundamental thing. It tells us that the block is not a flat, featureless slab, but a richly curved structure where geometry and matter are inseparable. Any hope of restoring a single universal now by appealing to gravity runs into this complexity. Instead, we are pushed further toward the view that reality is a four-dimensional whole in which different observers carve up time and space in different, equally valid ways. In the next part, we will stir quantum mechanics into this already strange mixture. Quantum theory brings genuine randomness and superposition into the picture, and many people hope that this might reopen the future or challenge the block view. We will examine how quantum probabilities sit inside a block universe, and whether an indeterministic physics really rescues the idea that the future does not yet exist. Up to this point, our story has been shaped mostly by relativity and thermodynamics. Both of those gently nudge us toward a block universe where events across time coexist in a four-dimensional structure. But there is another giant in modern physics that many people hope will break that structure open: quantum mechanics. In its most familiar form, quantum theory tells us that outcomes are not fixed in advance but genuinely probabilistic. That sounds, at first glance, like good news for anyone who wants the future to be open rather than already written into the block. Quantum mechanics began as an attempt to understand the behaviour of atoms and light, and it quickly revealed a world that does not fit neatly into classical pictures. Particles can spread out like waves, interfere with themselves, and exist in superpositions that only become definite when we perform a measurement. The theory allows us to calculate probabilities for different outcomes with astonishing accuracy. What it does not do, at least in its most common textbook form, is say which outcome will happen in a given run of an experiment. That is where randomness enters. Think of a simple example. You send an electron through a device that measures one of its properties, and the theory tells you there is a 50% chance of getting one result and a 50% chance of getting another. Those numbers are not signs of ignorance about some hidden knob you forgot to check. At least according to the standard reading, they are built into the fabric of the theory. When you repeat the experiment many times, you see a pattern that closely matches the predicted probabilities, but any specific result in any specific run is unpredictable in principle. If that is right, then the future cannot be fully determined by the past. Even if you knew every detail of the universe right now, you could only assign probabilities to future measurement outcomes, not fixed certainties. This is where many people see a possible escape from the block universe. If the future is not fixed, they argue, how can it already exist in space-time? Surely there must be something that is still unsettled, something that is not yet part of reality. Quantum randomness seems like the perfect candidate. The difficulty is that quantum mechanics describes more than just random jumps. Between measurements, the quantum state evolves in a smooth, deterministic way. The equations that govern that evolution take a current state and produce a precise future state, at least at the level of those abstract wave-like descriptions. The randomness enters only when we link the theory to concrete outcomes. That raises a question. Is the indeterminism a fundamental feature of reality, or is it a feature of how we, as observers, extract information from a deeper structure? Different interpretations answer that question differently. In the so-called Copenhagen-style interpretation, the quantum state is often seen as a tool for predicting measurement outcomes rather than a direct picture of reality. When a measurement happens, the state is said to collapse randomly to one of the possible results. If you try to draw a block universe that includes collapses, you get a space-time where certain events at certain times involve genuine randomness. The block still exists, but which block becomes real may depend on which random choices nature makes as the universe unfolds. In the many worlds interpretation, the story is almost the opposite. There is no fundamental collapse. Instead, the quantum state of the universe always evolves smoothly and deterministically. When you perform a measurement, the combined system of you and the apparatus and the particles splits into branches. In one branch you see one outcome, in another branch you see another. All branches exist in a larger structure. From this point of view, there is no single future that needs to be chosen. All possible outcomes that have non-zero probability are realized in different parts of the grand block. Other approaches, such as hidden variable theories, try to restore determinism in a more traditional way. They say that there are extra pieces of information, not captured by the standard quantum state, that fix which outcomes occur. We cannot access those hidden variables directly, but they steer the results behind the scenes. If such theories are right, then the apparent randomness of quantum mechanics is like the randomness of rolling dice when you do not know all the microscopic details. The universe might still be fully determined, even if we cannot predict everything in practice. What all these interpretations share is this: none of them straightforwardly restores a simple, growing present in which the future does not yet exist. Even when quantum events are truly random, that randomness does not automatically mean that the future is absent from the block. A block universe does not require predictability. It only says that whatever outcomes happen are part of spacetime. The block can contain regions where events have probabilistic causes just as easily as it can contain regions where events follow strict deterministic rules. Think about how we describe a coin toss after the fact. Before you flip, you may honestly say that the outcome is uncertain, even in principle. After the coin lands, you look and see that it came up heads. In a block universe picture, the event of that toss, including its specific result, is just one point in space-time. Your earlier uncertainty was a fact about your knowledge, not a gap in the block. Quantum randomness can be understood in a similar way. At one point along your world line, you can only assign probabilities. At a later point, you see which outcome your branch of the block contains. The many worlds view makes this even more explicit. In that picture, the block universe is not only four-dimensional in the ordinary sense, it also contains a branching structure of quantum histories. Every time a quantum event with several possible outcomes occurs, the state of the universe splits into multiple branches, each with its own consistent record. You, as an observer, ride along one branch and feel that a single future has been selected. But in the larger structure, all branches exist. The openness you felt was about not knowing which branch you would find yourself in, not about the non-existence of the others. Even in interpretations that keep collapse, you can frame the situation in block language. Instead of thinking of the block as fixed in advance, some physicists imagine it as a kind of four-dimensional history that is partially constrained from both ends. The equations and boundary conditions restrict what can happen, but there is still room for genuinely random events within that framework. When those events are realized, they pick out one specific history among many compatible ones. Once that history is in place, it can still be represented as a single space-time structure. So quantum mechanics complicates the block universe, but it does not easily overturn it. It introduces deep uncertainty into our predictions and invites multiple ways of thinking about reality. Yet the basic geometric idea that events can be represented as points along world lines in space-time remains intact. Whether those events unfold deterministically or involve randomness, they can still be embedded in a four-dimensional block. The question of whether the future exists is not settled by quantum probabilities alone. What quantum theory does do is sharpen the distinction between two different ideas that are often blurred. One is the existence of future events in space-time. The other is the possibility of predicting those events from present data. A future that already exists in the block can still be unpredictable in principle for observers inside the universe, especially if quantum randomness is real. From your perspective, the future remains open, full of branching possibilities. From the imagined outside view of the block, all those possibilities are realized in one way or another. In the next part, we will leave the level of particles and probabilities and return to something more personal. If the block universe is right, what does that mean for you as a persisting self? How does a person exist in a four-dimensional space-time where every stage of their life is just one more point along a world line? We will explore how identity, memory, and mortality look when you stop thinking of yourself as a point-like observer, moving through time, and start seeing yourself as an extended pattern in the block. By now we have stretched time, flattened it into diagrams, curved it with gravity, and sprinkled it with quantum uncertainty. All of that is fascinating until you suddenly realize there is something else sitting quietly in the middle of it. You, the person watching this. If the universe really is a four-dimensional block full of world lines, then you're not a point-like observer riding a conveyor belt called time. You're a long extended pattern in space-time. That sounds abstract, but it cuts right into how we think about identity, survival, and what it means to live a life. Start with something simple. Pick a memory from childhood, maybe sitting in a classroom or playing outside or hearing a song that still makes you nostalgic. When you call up that scene, it feels like you're reaching back to the same person you are now, just smaller and with different worries. In the everyday picture, that child is gone and only survives as traces in your mind. In the block universe picture, that child is still there as one stretch of your world line, as real as any other event in space-time. One way to imagine this is to think of your life as a long, twisting sculpture made of transparent glass. At one end is a tiny, fragile shape that represents your earliest moments. As you move along, the sculpture widens and changes, reflecting growth, learning, and experience. Near the far end, it thins and finally comes to a point. You normally see only a thin cross-section of this sculpture and call that the present. The block universe asks you to step back in imagination and see the whole shape at once. That whole shape is you. Within that sculpture, each cross-section is what some philosophers call a person stage, a version of you at a particular time, with a particular body and set of memories and character traits. No single stage has the full story, but they are tied together by strong connections. Memories link them. Physical continuity of your body links them. Gradual psychological change rather than sudden jumps links them. Identity becomes less about a mysterious soul and more about this chain of overlapping similarities along a world line. This view helps make sense of some old puzzles. Consider the classic question of the ship that has its planks replaced one by one over many years. At what point does it stop being the same ship? In the block picture, there is no sharp moment where identity flips. Instead, there is a continuous world tube of ship events, with each stage closely related to the previous one. You can choose to call the whole tube one ship, or to draw lines and say that after some point it is a new ship. The physics does not dictate the answer. It gives you the structure and leaves the label to you. The same goes for thought experiments about teleportation or copying minds. Suppose a machine scans your brain in perfect detail, builds an exact copy on Mars, and destroys the original. Is the person who wakes up on Mars still you? If you think of yourself as a single point-like thing that moves through time, this question can feel paralyzing. If you think of yourself as a pattern in space-time, you can instead ask how the world lines line up. Does the Mars pattern continue the same chain of memories and character traits? Does it occupy the role in the larger network of relationships that your Earth pattern would have occupied? None of this makes the questions trivial, but it shifts where the weight sits. Identity stops being an all-or-nothing secret property that clings to one stage and jumps to the next. It becomes a matter of how strongly different stages are connected. In the real world, change is slow enough that we rarely worry about this. You do not wake up each morning and wonder whether the person opening their eyes is really you or a replacement. The links of memory and habit are tight. The world line is smooth, so the sense of being a single continuous self remains strong. Then there is death. In an ordinary picture, death is a moment when a person drops out of existence. The light goes out, and what was once present becomes nothing. In the block universe, the story looks different. Your world line has a final segment, a last moment in space-time. After that, there are no more stages of you. But all the earlier stages remain as parts of the block. The child watching rain on a window, the teenager discovering a favourite song, the adult making hard decisions. None of those are erased. They are fixed coordinates in space-time. People react very differently to this. Some find it strangely comforting. If all the moments of a life always exist in the block, then nothing that ever happened between you and someone you love can be undone. Those shared events are woven into the structure of reality as securely as the orbit of a planet. Others find it cold. They want a future that is not yet written, a space where new existence can be created rather than just revealed. The block universe does not satisfy that desire. It says the story is already there, even if you do not know all the chapters. There is also the question of responsibility. If your entire life is a fixed world line, is it fair to praise or blame you for what happens along it? On one view, yes, because your choices are part of that line. The event of you deciding to help someone or to harm someone is not an external force acting on you. It is you. It expresses your character at that stage. To say that you could have done otherwise in a deep sense may be tricky in a block universe, but to say that your actions belong to you is still meaningful. They are located on your world line, not on someone else's. In daily life, we already treat identity as something that stretches over time but can also fray. We worry about diseases that affect memory and personality because they weaken the links between stages. We're uneasy about systems that could copy or simulate a person because they create branching patterns rather than a single simple line. The block picture does not create these worries, but it frames them in geometric terms. It invites you to see yourself as a shape in space-time whose internal structure can be more or less coherent. One practical consequence of this view is a shift in how you might think about your own life story. If you imagine your world line laid out, you can ask yourself what kind of pattern you want it to have. How do you want the early segments to relate to the later ones? What arcs or themes do you want someone to see if they could trace the whole line? Even if the block is fixed at the fundamental level, you still experience decisions as open. You still face choices without knowing how they turn out. From inside the story, that feels exactly like authorship. In the next part, we will look more closely at one of the most striking asymmetries along your world line. You remember the past, but not the future. You keep records of what has happened, but almost none of what will happen. In a block universe where both directions exist, that is a surprising fact that demands an explanation. We will explore how entropy, information, and the formation of records work together to a memory in only one direction along the block, even though the block itself does not single out a preferred direction. Think about how lopsided your experience of time is. You carry a rich collection of memories of what has already happened. You have photos on your phone, scars on your body, messages in your chat history. All of these point backward along your world line. Yet you have almost nothing comparable that points forward. No photographs from next week, no diary entries from next year, no scars from accidents that you have not yet had. In a block universe where past and future events all exist in space-time, this asymmetry is striking. If both directions along your world line are equally real, why do you only have detailed information about one side? Why do you remember the past but not the future? Why do we find fossils of long-dead creatures, but not fossils of animals that, from our perspective, have not yet lived? The answer reaches deep into the physics of entropy and information. A memory is a physical thing. It might be a pattern of connections and activity in your brain. It might be ink on paper, magnetized spots on a hard drive, or tiny pits on a disk. In every case, a memory is a low-entropy structure that correlates with some other event. The pattern in your brain lines up with a pattern in the world. The streak of soot on a ceiling lines up with the fact that there was once a flame beneath it. Creating such correlations is not free. It requires energy, and it usually increases entropy overall. When you store a new memory, your brain burns chemical fuel and produces heat. When a camera takes a picture, it uses battery power and generates waste heat in its electronics. These processes take a world that is somewhat ordered and rearrange part of it into a more ordered pattern that carries information, while increasing disorder elsewhere. The total entropy goes up, even though a small pocket of lower entropy appears as a memory or record. Because the universe started in a low entropy state, as we discussed earlier, there is room for these little islands of order to form as time moves forward along the thermodynamic arrow. Matter clumps into stars and planets. Chemical gradients appear. Life evolves and builds nervous systems and tools that can store information. All of that is possible because entropy in the wider environment is rising. Records of earlier states are physical byproducts of this general trend. They are an expected feature of a universe marching away from a special beginning. Now imagine trying to build a record of a future event instead. To store information about something that, from your standpoint, has not yet occurred, you would need a pattern that is precisely tuned to match what will happen. But the growth of entropy works in the opposite direction. As you move toward what you call the future, there are more and more ways for matter and energy to arrange themselves. The number of possible detailed futures that fit your current large-scale state is enormous. There is no simple, reliable way to pick out the exact one that will occur and encode it in advance. In a block universe, the future event is already there. Its details are fixed along your world line, but the physical processes that form records where you are now do not have access to that information. They are local. They respond to what is in their past light cone, not to what lies ahead. Signals travel at finite speeds. Causes leave traces that spread outward. Those traces can reach you from past events and be frozen into memories and photographs. They cannot arrive from events that are still to come along your world line. This is tied closely to the way entropy gives time a direction. When you look back, you see low entropy states that have left many durable marks. A childhood home preserved in pictures, layers in a rock that record ancient climates, light from distant galaxies that set out billions of years ago and only now reaches your telescope. These are all examples of information flowing from lower entropy, past configurations into higher entropy present ones. The records accumulate in the direction of increasing entropy. You can test this asymmetry in small experiments. If you drop a glass and watch it shatter, you can pick up the pieces and infer roughly what the original shape must have been. The pattern of fragments is a messy, higher entropy state that still carries clues about the earlier lower entropy arrangement. But if someone handed you a random pile of glass shards and asked you to reconstruct the next few minutes of their history, you would have no chance. There are too many possible futures consistent with the pile. The traces do not point that way. The same logic applies to your inner life. When you remember an experience, you are reading out information that was stored when you were in a low entropy relationship with that past event. Your brain laid down patterns while you were there, using energy and increasing entropy overall. Those patterns persisted and can now be reactivated. To remember the future in the same way, your brain would need to contain patterns that line up with events that have not yet sent any influences your way. There is no physical channel by which those correlations could have been formed. So in the block universe picture, memory and records do not tell you which times exist. They tell you which times are connected to your current state through physical processes that follow the entropy gradient. The past is full of such connections. The future is not, at least not yet from your point of view. That is why you feel as though the past is fixed and known while the future is open and unknown, even if both directions are equally real in the block. The asymmetry of information rides on the asymmetry of entropy. There is something almost poetic about this. The universe begins in a special low entropy condition. As it evolves, complexity and structure emerge. Within that unfolding, small systems like brains and cameras arise that can form records of what has happened. Those records allow stories to be told, histories to be written, selves to be knit together out of sequences of events. All of that meaning flows in the same direction as the physical arrow of time. It is as if the block universe contains a built-in narrative direction that agents like us naturally follow. At the same time, this picture gently reminds us that our sense of the past is fixed and the future is open is not the last word on reality. It is a reflection of where we sit in the block and how information has reached us. If you could somehow take the view of a being outside spacetime and look at the entire block at once, you would see records and memories as structures scattered throughout, each one pointing toward one side of its own local entropy gradient. No single perspective would be privileged. Each world line would carry its own one-way arrow. In the next part, we will step back from physics for a moment and look at the landscape of ideas that try to resist or reshape the block picture. Growing block theories, versions of presentism that add hidden structure, and other attempts all aim to recover a universe where the future genuinely does not yet exist. We will explore why these alternatives remain attractive, what they cost in terms of simplicity and fit with relativity, and why the debate over time's true nature is still very much alive. At this point, the block universe can feel almost unavoidable. Relativity joins space and time. Entropy carves a one-way gradient inside space-time. Quantum mechanics complicates prediction, but does not clearly break the four-dimensional picture. It might seem as if the case is closed, yet it is not. Many philosophers and some physicists still resist the idea that past, present and future all equally exist. They propose alternative pictures that try to keep something like a growing or uniquely real present, even while respecting modern physics as much as possible. One of the most popular alternatives is called the growing block view. It keeps part of the block universe but not all of it. In a growing block, the past and the present both exist, laid out as a thick slab of space-time. The future, however, does not yet exist. As time passes, more and more of the future becomes real and gets added to the block. You can picture it as a book that is being written from front to back. Earlier chapters are finished and unchangeable. The current chapter is being set down right now. Later chapters have not yet been drafted. This view appeals to people who want to respect the reality of the past, while preserving a sense of becoming. It lets you say that dinosaurs and ancient galaxies are as real as your childhood, but that tomorrow truly is not here yet. The growing block captures some of the pull of both eternalism and presentism. It offers a world that is partly completed and partly under construction, with the construction front moving forward as time passes. However, once you place this picture next to relativity, problems start to appear. Growing block theory needs a clear rule for which events are already in the block and which are not. It needs a sharp edge between the real and the merely potential. In Newtonian physics, that edge could be the global present defined by absolute time. In relativity, there is no unique way to define such a global present. Different observers slice space-time into moments of now in different ways. So growing block theorists often end up smuggling in some hidden preferred slicing that the equations do not reveal. That move brings them close to certain versions of presentism that also rely on an unseen cosmic time. Presentism, in its pure form, says that only the present exists. The past is gone, the future unreal. To make this compatible with relativity, some presentists propose that there is a fundamental foliation of space-time into slices that represent the true present at each stage. These slices might line up with the time coordinate of cosmology in a roughly expanding universe, or with some deeper structure we have not yet discovered. From the standpoint of the basic equations, this looks like extra baggage. Einstein's theories treat all inertial frames as equally valid. No experiment has yet revealed a special frame that plays the role of an absolute rest or absolute time. Adding one in secretly can feel like returning to an ether that has no observable effects. Defenders of these views reply that physics does not forbid extra structure. It simply does not need it for calculations. Metaphysics, they argue, is allowed to go beyond what is strictly required to compute predictions. There are also more subtle presentist strategies. Some try to make the present a local rather than global notion. Instead of a single cosmic slice, they define the present as a small neighbourhood around each event, connected by signals that could in principle be exchanged. Two distant regions that cannot yet have communicated are not in the same present. This sidesteps the need for a rigid global slicing, but at a cost. Reality becomes patchy, with no single common now that spans the observable universe. Others take a different approach and challenge the idea that physics alone should guide our picture of time. They point out that conscious experience seems to present time as a flow with a privileged now. They worry that the block universe reduces this rich experience to a mere byproduct of geometry. On this line of thought, any adequate theory of time must make sense not just of clocks and world lines, but also of what it is like to live a life. If the block cannot do that convincingly, then perhaps it is incomplete. Eternalists answer that they are not ignoring experience. They are explaining it in terms of physical and psychological processes inside the block. The flow you feel is tied to memory, prediction, and entropy, not to an extra moving layer of reality. They argue that adding an objective passage of time on top of that does no explanatory work. It makes no new predictions, fixes no contradictions, and complicates the picture. For them, the block universe is attractive precisely because it is simple and closely aligned with the structure of well-tested theories. There are also hybrid ideas that try to merge elements from several views. Some propose that the laws of physics might be evolving along with the universe, so that the future is in some sense more open than the past, even if spacetime still has a block-like character. Others suggest that quantum processes might pick out a preferred slicing of spacetime that could underwrite a real present, especially in interpretations where wave function collapse is fundamental. These proposals are speculative, and none has yet gained clear empirical support, but they show how unsettled the terrain remains. Underneath all these technical debates are deeper questions about what we expect from a picture of reality. Some people prize alignment with physics above all. For them, any view that sits awkwardly with relativity or thermodynamics is suspect. Others prioritize capturing the phenomenology of time, the vivid sense of flow and becoming. For them, a theory that fits equations but leaves experience feeling like an illusion may seem unsatisfying. Still, others care most about preserving certain intuitions about morality or free will, and they judge views of time partly by how well those intuitions can survive. The block universe scores highly on simplicity and fit with relativity. It treats space-time as the basic object, and explains many puzzling features of time as emergent patterns within that object. It meshes well with the geometric language of modern physics, but it asks you to accept that the future exists as firmly as the past, and that the flow you feel is not written into the cosmos. Growing block and presentist views keep more of that intuitive flow and genuine becoming, yet they typically pay a price in complexity or in conflict with the symmetry of the laws. Because none of these positions leads to different experimental predictions at present, the debate stays in the realm of interpretation. It is less like arguing about whether a particle exists, and more like arguing about the best way to read a story that can support several metaphors at once. Does the universe resemble a completed book, a book that is still being written, or a single page that keeps replacing itself? Each picture highlights some aspects and hides others. None has been decisively crowned by data. What we can say is that modern physics has pushed the conversation far beyond where it stood a century ago. Relativity and thermodynamics have made it very hard to maintain a naive version of presentism in which there is a single, absolute, moving now. Any view that holds on to becoming has to be subtle and carefully built. Eternalism and the block universe, in turn, have grown from fringe ideas to central players in serious discussions about time. In the next part, we will return to the laws themselves and ask what it means for them to govern a block, rather than a universe that comes into being moment by moment. If the block is real all at once, how should we think about laws, causation, and the idea that one event makes another happen? We will explore how physical laws can be seen as global constraints on the shape of space-time and what it means, in that setting, for anything to happen at all. When we learn physics in school, it is usually told as a story about things evolving. You have a state of the world now. You plug it into the laws. They tell you what the state will be a moment later. Then you repeat. The universe looks like a giant calculation that proceeds step by step. That picture fits nicely with our sense that time flows, but it starts to feel awkward once you take the block universe seriously. If space-time is a four-dimensional whole that already exists, what does it even mean for laws to push things from past to future? One way to answer is to shift how we think about laws. Instead of rules that drive the universe forward in time, laws can be seen as constraints on the shape of the block. They are like conditions that any possible space-time must satisfy if it is to count as a physically allowed world. The equations of general relativity, for instance, relate curvature and energy at every point in space-time. They do not need the universe to be generated slice by slice. They simply say that the geometry and the matter content have to fit together in a consistent pattern across the whole block. To make this more concrete, think of a map of a mountain range. The lines on the map show where the land is high or low. The rules of geology and erosion tell you that certain kinds of shapes are allowed and others are not. You will not find a perfectly sharp spike of rock 1,000 kilometers tall standing on a paper-thin base. The structure of rock, gravity and time will not permit it. Those rules do not need the mountain to be built 1 meter at a time. They describe the space of possible landscapes and rule some of them out. In the same spirit, physical laws can be thought of as rules about which four-dimensional spacetimes are possible. They say that if the block has this distribution of matter here, it must have that kind of curvature there. If particles interact in this way at one event, then there must be matching patterns of fields at neighbouring events. When physicists talk about solving the equations, they are really finding possible blocks that satisfy the constraints. Once a solution is found, it is a complete history laid out in space-time. Nothing in the mathematics is literally watching it unfold. Of course, for calculation we often pick an initial slice, specify data there, and then use the equations to compute what happens next. This still works perfectly inside a block view. The initial data on the slice and the laws together select one allowed spacetime history from many candidates. But that is a method of discovery, not a description of how reality grows. It is like being handed part of a map and using the rules of cartography to infer the rest. The full map was always there in principle. We just did not yet know its details. Causation needs a similar reinterpretation. In everyday talk, we say that one event makes another happen. Striking a match causes it to light. Pressing a key causes a letter to appear on your screen. In a block universe, all of these events are simply points in space-time connected by lawful patterns. The match strike and the flare of flame stand in a certain relation. The neural activity in your brain and the motion of your fingers stand in another. Instead of causes pushing effects into existence, we have networks of events that fit together according to the constraints of the laws. This might sound as if causation disappears, but that is not quite right. It changes from a fundamental ingredient to something like a useful way of reading the block. When we say that striking the match causes the flame, we are noticing that there is a reliable pattern. In blocks that contain match strikes of a certain kind, there are usually nearby events of ignition, and information flows from the first to the second, but not the other way. We choose to label this asymmetric pattern with the language of cause and effect. The asymmetry still has a physical basis. It is tied to entropy and the arrow of time. In most ordinary situations, information about earlier events is present in later stages, but not vice versa. The structure of the block is such that you can often predict the future from the past, at least in broad strokes, but you cannot generically reconstruct every detail of the past from only future data. This gives causal talk its familiar direction. Causes sit in what we call the past. Effects sit in what we call the future. The direction is about the way information and entropy behave inside the block, not about a hidden force pushing reality forward. Another helpful comparison is with a story printed in a book. All the sentences on all the pages exist at once in the physical object. Yet within the story, some events are earlier and some are later. Some actions lead to consequences. The author may have written the ending long after the beginning, but once the book exists, the logic of the plot runs in a certain direction. Characters make choices, those choices have outcomes, and we as readers talk naturally about causes and effects inside the narrative, even though the book itself is not changing. The block universe invites us to see reality in a similar way. The four-dimensional space-time is the complete story. Physical laws are like rules of grammar and plot that shape which stories are allowed. Causation is the pattern we notice when we trace lines through the story that run from low entropy beginnings to higher entropy outcomes, carrying information along. From inside that story, it feels completely natural to say that one event makes another happen, even though the entire pattern is already part of the block. This has an interesting consequence for how we think about explanations. When you ask why something happened, you might expect an answer in terms of earlier events that caused it. In a block view, you can also think of explanations as locating the event within a larger pattern that satisfies the laws. The reason a planet follows a certain orbit is not just that it was kicked just so in the past. It is also that the entire world line of the planet fits into a space-time geometry that solves the gravitational equations. The law-based explanation is global, not purely step by step. Some philosophers call this a shift from a dynamic to a geometric way of thinking. Instead of imagining the universe as a machine that ticks forward, we imagine it as a structure that simply is. Time is one of the dimensions of that structure. The machine picture and the structure picture are not enemies. They are two languages for talking about the same underlying reality. For many practical purposes, the dynamic language is easier. For deep questions about time, the geometric language reveals patterns that the other tends to hide. You might worry that this makes the word happen meaningless. If everything that ever happens is just a point in a static block, is happening an illusion as well? One way to ease that worry is to remember that you are part of the block too. Your experiences of change, of events unfolding, are themselves sequences of events in space-time. Saying that something happens is a way of describing how those sequences are arranged. In the block universe, happening is not the universe changing. It is you moving along your world line and registering different events in order. In the final part of this journey, we will bring all of these threads back to the human level. If laws are constraints on a block, if causation and happening are patterns within it, and if our sense of flow is a story the brain tells as it rides the arrow of time, what does that mean for free will, responsibility, and the search for meaning? We will try to live, at least for a few moments, with both pictures at once, the completed map and the unfolding journey, and see how that double vision might change the way you think about your own life. By now, the block universe can feel like a cold verdict. If every event in space-time already exists, where does that leave your sense of choice? When you stand at a crossroads and agonize about what to do, are you really shaping your future, or just discovering the next page in a book that was written long ago? It is easy for the block to slide into a picture of fate, where nothing you do truly matters. But that reaction, while understandable, quietly smuggles in a way of thinking that the block does not actually require. Fatalism says your choices are irrelevant. No matter what you decide, the same outcome will happen. The block universe says something different. It says that your choices are part of the outcome. The event of you deciding one way rather than another is a real feature of the space-time structure. If you had chosen differently, the block would be different. There is no sense in which the future is fixed independently of what you do. Instead, what you do is one of the things that fixes the future. Seen this way, free will becomes less about breaking the block and more about understanding your place inside it. You're not an outside force trying to bend a static cosmos. You're one of the patterns etched into space-time. Your values, habits, and reasons live along your world line. When you face a decision, the outcome is determined by a complex mix of all those factors, plus the circumstances you find yourself in. That mixture is not something apart from you. It is you, extended in time. Some philosophers call this a compatible view of freedom. On this view, you are free when your actions flow from who you are, not from external compulsion or random twitching. If your choice to help a stranger comes from your concern for them, your understanding of the situation, and your own long-term commitments, then it expresses your agency, even if the block description says that this event was part of the structure all along. The fact that the choice has a place in space-time does not make it any less yours. Part of the discomfort comes from mixing two standpoints. From outside the story, looking at the whole block, everything is laid out. From inside the story, at a particular point along your world line, you do not know what comes next. You face real uncertainty, make real trade-offs, and feel genuine pressure. When you choose, you close off some possibilities and open others. That experience is not erased by the block. It is one of the things the block contains. The same event can be both a fixed point in space-time and a lived turning point for the person passing through it. Think of reading a mystery novel for the first time. The ending already exists in the book. Every page is printed. Yet as you read, you have no idea who did it. You form suspicions, revise them, and feel surprise when the truth is revealed. Your experience of suspense is not fake just because the pages already sit bound together. The block universe says something similar about your life. The fact that there is a complete space-time story does not trivialize your suspense, your effort, or your growth as you live that story from the inside. Responsibility fits naturally into this picture. When we hold someone responsible, we look at whether their actions came from their character and understanding, whether they could have responded differently in nearby circumstances, and how their choices affected others. All of that is about patterns along world lines. Some parts of the block contain agents who act thoughtfully and care about consequences. Other parts contain agents who act recklessly or cruelly. The block view does not flatten those differences, it records them. It is still meaningful to say that a person is accountable for what lies along their own path. You might still worry that in some deep sense you could not have done otherwise, because in the actual block you did what you did. Here it helps to recall that physics by itself never tells you what could have happened. It only tells you what did happen in this particular world, and which other patterns would have been allowed under the same laws. When we talk about what you could have done, we are comparing this block with other possible blocks where conditions were slightly different. That comparison is part of moral and practical reasoning, not a literal claim that the actual block contains multiple outcomes for one event. Meaning is the other big concern. If your life is a fixed world line, does it still matter how you live? For many people, meaning is tied to change. You want to grow, to repair mistakes, to help others, to leave something behind that outlasts you. The block universe does not take those aims away, it reframes them. A meaningful life becomes a certain kind of pattern in space-time, one where challenges are faced with courage rather than fear, where relationships deepen rather than crumble, where suffering leads to insight or solidarity rather than only bitterness. You can even turn the block view into a tool for reflection. Imagine your world line as a path you could see from above. How would you want it to look? Would you see long stretches of fear and avoidance, or arcs of slow but real change? Would you see moments where you stood up for someone when it was hard, or mostly moments where you took the easy way? Picturing your life as a shape in space-time can sharpen questions you already feel. It does not answer them for you, but it invites you to think in terms of coherence and direction rather than isolated moments. There is also a quiet comfort some people find in this picture. If every event in your life always exists in the block, then no joy is ever truly erased. The moment you first met someone important, the time you laughed until you could not breathe, the small kindness that changed your day, All of those are permanent features of space-time. They are not slipping away into nothing. They are fixed points that will always be part of the universe's structure, even when you have moved far beyond them along your path. At the same time, the block view can feel heavy. If your future mistakes already exist somewhere in space-time, it is tempting to feel resigned. Yet resignation is itself a stance you can take or refuse. It is another possible pattern in the block. Whether you lean into responsibility, keep trying to do better, and care about others is not decided by the mere existence of the block. It is decided by the detailed shape of your own world line, which includes your attitudes toward these very questions. Living with both pictures at once may be the most honest stance we can take. On one level, you treat the future as open, because from your position you genuinely do not know what comes next. You deliberate, you choose, you act. On another level, you can recognize that physics invites a view in which the entire tapestry of events exists in space-time, and that your journey is one thread woven through it. Holding these together does not solve every philosophical puzzle, but it can enrich your sense of what it means to be a finite, choosing being in a vast and structured cosmos. In the final part, we will step back and look at the whole path we've travelled, from the death of a universal now to the possibility of a block universe, from entropy and quantum uncertainty to memory, identity and meaning. We will try to see time with new eyes, and ask how this strange double vision might change the way you carry your own brief segment of world line through the unfolding of your days. Take a breath and notice this moment. The device in your hand, the sounds around you, the faint echo of the last sentence still hanging in your awareness. It feels like the center of reality. Everything you remember is behind you. Everything you hope for is ahead. This is the only point that seems to truly exist. Yet we have spent this entire journey exploring a picture in which that feeling is only one way of slicing a much larger whole. A universe where your birth, this instant, and your final day all sit together in a four-dimensional space-time. We began with the everyday idea that time is obvious. There is a single universal now. The past is gone. The future has not arrived. Then special relativity undermined that simple picture. The speed of light stays the same for every steady moving observer, and to protect that, space and time must bend. Simultaneity becomes relative. Two people walking past each other can disagree about what is happening right now in a distant galaxy. The Andromeda paradox pushed that idea to the edge and forced us to ask whether a single cosmic present makes sense at all. From there, Minkowski invited us into a new way of seeing. Space and time are not separate containers. They fuse into space-time. Events become points in a four-dimensional arena. Each life is a world line weaving through that block. Instead of the universe being built moment by moment, reality looks more like a finished tapestry. Past, present and future become different regions of one structure. The block universe, or Eternalism, stepped forward as a bold interpretation. It does not change the equations, it changes what we think those equations are telling us about reality. This view collided with older philosophical pictures. Presentism tried to preserve a moving spotlight of reality that shines only on the present. Growing block ideas tried to keep the reality of the past, while letting new slices of space-time be added as time passed. Relativity gave these views a hard time. Without a unique global now, it becomes difficult to mark which events are real and which are not. Eternalism embraced that difficulty and suggested a simpler story. Everything that ever happens exists in space-time. Different observers simply carve the block up in different ways. Einstein's remark about the distinction between past, present and future being a stubborn illusion took on a deeper meaning against this backdrop. He was not dismissing experience. He was pointing out that the flow we feel is not part of the basic geometry. The equations of relativity do not mention a moving now. They describe relations between events across space-time. The feeling of passage lives in the minds of creatures who trace world lines through that structure, not in the structure itself. To understand that feeling, we turned inward. The brain does not experience razor-thin instants. It lives in a thickened now, a specious present that blends a short stretch of recent time into one unified moment. Neural circuits integrate signals, store traces of what just happened, and generate predictions about what is about to happen. Memory and expectation overlap. From the inside, that overlap feels like motion, a continuing story rather than scattered frames. The flow of time in your awareness is a construction, assembled from many small processes that operate along your world line. We then stepped back out to the cosmos and asked why time has a direction at all. The basic laws are almost symmetric under time reversal, yet the world we see is not. Eggs break but do not unbreak. Glasses shatter but do not leap together. Entropy, the measure of how many microscopic arrangements fit a large-scale state, becomes the key. Low entropy past, high entropy future. The second law of thermodynamics tells us that systems tend to move from rare, ordered states to typical, disordered ones. That trend defines an arrow of time inside the block. In the block picture, this arrow is not a force that pushes the universe from earlier slices to later ones. It is a pattern in the distribution of states across space-time. Near the edge we call the Big Bang, entropy is extraordinarily low. As you move away from that region along typical world lines, entropy rises. Records and memories form in that direction. Information about earlier states is carried forward, but information from later states does not reach back. Your sense that the past is fixed and the future open is rooted in that asymmetry of records, not in the non-existence of future events. Quantum mechanics added its own twist. Randomness, superposition, branching interpretations, hidden variables. At first glance, quantum uncertainty seems to promise an open future. Yet even there, the block universe can absorb the shock. Whether the world is deterministic, whether it branches into many quantum histories, or whether some events are fundamentally random, the outcomes that do occur can still be represented as points in space-time. The block does not demand predictability. It only says that whatever actually happens has a place in the structure. Quantum theory changes how we talk about possibility and prediction, not so clearly what exists. That raised a more personal question. In a block universe, what is a person? You're no longer a moving dot that carries a mysterious essence forward. You're an extended pattern, a long world line with rich internal structure. Each stage of you is a cross-section of that line, carrying memories of earlier stages and expectations about later ones. Identity becomes a matter of how strongly those stages are tied together by continuity of body, psychology, and relationship. Death becomes the last point of the line, not the erasure of all its earlier points. We saw how memory and records fit into this framework. They are physical structures, low-entropy patterns that encode information about other events. They form as the universe moves along its entropy gradient. That is why they point backward rather than forward. In the block, the future exists, but your present state is not wired to it by the same chains of influence that connect you to the past. Your arrow of memory runs one way because the cosmic arrow of entropy does. In that sense, the narratives you tell about your life are written along the same direction as the growth of disorder in the wider universe. Then we reframed laws and causation. Instead of laws being engines that push the universe from one time to the next, they become constraints on the shape of the block. Only certain space-time structures are allowed. Causation becomes the pattern we notice when events are linked in stable, asymmetric ways that line up with the entropy arrow. The match does not cause the flame by shoving reality forward. The match and the flame are part of a lawful pattern across space-time, and from inside that pattern, following the temporal direction picked out by entropy, it makes sense to tell a story of cause and effect. Finally, we turn to free will, responsibility, and meaning. The worry that the block universe makes everything pointless rests on a particular picture of freedom. A picture where you must somehow stand outside of time and choose among genuinely unreal futures. The block picture suggests a different understanding. Your choices are events in space-time, They express who you are. They shape what lies along your world line. From the inside, you experience uncertainty, weigh reasons, and decide. From the outside, those decisions appear as part of the structure. Both views describe the same reality at different levels. So what do you do with all of this? One option is to treat the block universe as a purely intellectual curiosity, an odd consequence of modern physics that does not touch your daily life. Another option is to let it reshape how you see that life, without trying to live as if you float above space-time. You can carry both pictures at once. When you plan your day, you lean into the lived sense that the future is open. When you step back in reflection, you can imagine your life as a whole pattern and ask whether that pattern reflects the values you care about. You might find comfort in knowing that every moment you have lived is, in this picture, an enduring part of reality. The small kindness you offered, the effort you made when no one was watching, the quiet beauty of an ordinary afternoon, none of that is ever undone. It is woven into the structure of space-time. You might also feel a renewed seriousness, knowing that all your actions are in a sense inscribed. They are not trials in a rehearsal, they are parts of the final cut. Most of us cannot walk around thinking in 4 dimensions all the time. We are built to navigate the one-dimensional stream of experience that the brain presents. That is fine. The point of this journey is not to replace your lived sense of time. It is to add another layer of understanding, to know that beneath the flow you feel there is a deeper geometry, that the story you are living is one thread in a vast tapestry, and that physics gives us hints about the shape of that tapestry, even if it cannot tell us how to feel about it. So as you step back into your own life after this video, you can try a small experiment. Every now and then, pause and imagine your current moment as one point on a long world line. Imagine earlier points shining behind you, and later points waiting ahead, all part of a single shape. Then return to the ordinary sense of flow, and make your next choice as you always do, with limited knowledge and real concern. Holding both visions together is not easy, but in that tension, there is a new way of seeing time, and perhaps a new way of seeing yourself,